The electronic configuration of transition metals are a little different from the first 18 elements which we have learned in the previous video. But before diving into this, let's first learn about shorthand notations. As its name suggests, shorthand notations are a short form of writing the electronic configuration. Its format consists of the last noble gas in brackets plus the rest of the subshells. Using magnesium as an example, this is its electronic configuration: 1s2, 2s2, 2p6, and 3s2. Its shorthand notation is brackets neon 3s2. It's quite easy to understand. If we look at the configuration of neon, which is 1s2, 2s2, 2p6, the shorthand notation is basically substituting the subshells with an element. Understanding the shorthand notation can save a lot of energy writing all the subshells and only focus on the subshells at the most outside principal quantum shell. Let's go back to transition metals. We have learned that the first two groups represent the S shell and the last 6 groups represent the P shell. In this video, we will learn about the D shell elements, which is in the middle. Let's attempt to write the shorthand notation of transition metals. Using iron as an example, we first find and write its previous noble gas in brackets. In this case is argon. Then at the 4th quantum shell there are 2 S shell electrons, so we write 4s2. Then we find iron locating at the 6th position at the D section. If we use the previous logic, it will be 4d6, but in fact it's 3d6. It is a little counterintuitive, but this is due to the fact that the 3d shell has a higher energy than the 4s shell. So the electrons will first fill in the 4s shell before it fills in the 3d shell. Keep that in mind while writing the configuration of elements that has a d shell. There are also a few exceptions that you must remember that does not follow the pattern. Instead of 3d4, 4s2, chromium has a configuration of 3d5, 4s1. Similarly, copper has a configuration of 3d10, 4s1. Ionization energy is also a big topic in Chapter 3. Its definition is the energy needed for an atom to form an ion by removing an electron from the atom, or in simple words, it is a measure of how difficult is it to remove an electron from the atom. There are also a few terminologies you have to learn. The first ionization energy is the energy needed to remove one electron from an atom to form a +1 ion. Similarly, the second ionization energy is the energy needed to remove one electron from an atom to form a +2 ion. It is not hard to find the pattern. The nth ionization energy is the energy needed to remove one electron from an atom to form a +n ion. Here is an ionization energy trend graph of sodium. As the charge of the atom increases, the energy needed also increases. Occasionally, there are also big energy leaps like between first and second ionization energy. We will discuss about why at the next page. There are a range of factors that affect the ionization energy. Firstly is the nuclear charge. The bigger the charge, the more energy is needed. This is because if the nucleus has a bigger charge, it exerts a bigger attractive force towards its electrons. Therefore, the electrons become harder to remove. Secondly is the distance between the electron and the nucleus. This is because the electromagnetic force between the proton and the electron decreases as the distance increases. With less pull from the proton, it becomes easier to remove the electron. Thirdly is the shielding effect from the inner electrons. The outer electrons are easier to remove because the electrons are repulsive to each other. The outer electrons endure the repulsive force of the inner electrons and consequently become easier to remove. Lastly is spin pair repulsion. Electrons can either spin clockwise or anti-clockwise. Electrons with similar spins repel each other, which suggests that the repelled electron is easier to remove. Knowing the factors that affect ionization energy, we will then take a look at the ionization energy trends. Firstly, ionization energy increases across the period. This is because the nuclear charge increases, while the distance and the shielding effect remains relatively constant. Secondly, ionization energy decreases down a group. This is because the nuclear charge remains constant, while the principal quantum shell increased, therefore resulting in an increase in the distance between the nucleus. The inner electrons also increase, which meant that there is a stronger shielding effect which makes the repulsive force increase. Thirdly, the ionization energy decreases when the electron goes into a new subshell. This is because the distance between the nucleus increases, and there is an increase of repulsive force from the electrons in the previous subshell. Lastly, ionization energy also decreases when the electron is lone. This is due to the spin pair repulsion. If we look at the graph, we can see that oxygen has a lower first ionization energy than nitrogen. This is because in oxygen, there are 2 lone electrons in the p shell. If you draw the box form of its p shell, you can see that there are 2 electrons spinning in the same direction. This creates a repulsive force, which makes the electron easier to remove. Thank you for watching this video. Stay tuned in this channel for more A-level chemistry videos.